So, how does AI actually read? I mean, it doesn't have eyes, right? And it certainly doesn't understand letters and syntax the way you and I do. So, when you type a prompt into a chat box, how exactly do these models process human language?
When you type a simple phrase, like hello world, the AI doesn't see words at all. Instead, it sees sequences of numbers, things like 1533.9 and 1917. It literally translates our language into numerical tokens, functioning almost exactly like a secret numerical code. Welcome to this explainer. Today, we're exploring the absolute magic engine powering tools like ChatGPT. We're going to break down the exact mechanics of how large language models take our text, turn it into math, and use probabilities to generate incredibly human-sounding text. Okay, let's dive into this. Here's our structured roadmap. First, we'll look at the language of AI, then 3 ways to tokenize, third is the probabilistic edge, and finally, controlling AI creativity.
Starting with part 1, the language of AI.
To really understand how AI ingests the massive, overwhelming amounts of text on the internet, we have to look at what's called a windowed sequence. Since models can't read the whole internet at once, they process text in fixed-size overlapping chunks. It's very much like a human reading a massive 1,000-page book, just one single page at a time. It just keeps sliding that window forward.
And that brings us to this incredibly dramatic number, 100,277. Why does that matter? Well, that is the exact vocabulary size of GPT-4. Out of all the infinite combinations of letters and words on the entire internet, the model has compressed our language into roughly 100,000 unique numerical tokens. That number represents the vast probabilistic space the model has to navigate every single time it decides what word to say next.
Moving right along to part 2, 3 ways to tokenize.
Let's look at the specific mechanics of how human text gets chopped up into those numbered tokens. Seriously, think of it like building with Lego blocks. Our first method is byte pair encoding, or BPE. It starts with raw characters, then algorithmically finds the most frequent pairs, say the letters L and O, and merges them. It constantly merges the most frequently used Lego pairs to efficiently build complete tokens. And this frequency-based merging, it's the actual engine behind OpenAI's GPT models. Now, what's really interesting about this slide is how WordPiece takes a totally different approach. Instead of just merging tokens based on how often they appear next to each other, it chooses merges based on probability improvement. It essentially asks the math, hey, does snapping these specific Lego blocks together probabilistically improve the language model's likelihood of being correct? By evaluating machine learning likelihood rather than just frequency, it makes the model remarkably smarter, which is exactly why it's the tokenization engine behind Google's BERT models. Then we have sentence piece. Sentence piece treats text as completely raw data, spaces included, and learns the tokens automatically. Think of this like dumping raw Lego blocks onto a table with absolutely no pre-split rules or instruction manuals. The model simply learns language-independent patterns directly. This fully automatic approach is heavily used in modern LLMs like Llama. And this brilliantly illustrates the differences. To recap our 3 methods quickly, BPE focuses on the most common pairs, WordPiece focuses on probability-based model improvement, and Sentence Piece learns automatically from raw text. Keep these distinct approaches in mind as we step away from tokenization and jump into the heavier math of the neural network. Which brings us to part 3, the probabilistic edge. Okay, so now that we know how text becomes tokens, what actually happens mathematically to generate an output? Well, the first thing the neural network does is produce logits. To completely de-jargonize this for a second, logits are simply the raw, unnormalized scores that the model outputs for every possible next token in its vocabulary. It is literally just the raw score the model assigns to guess which of those 100,277 Lego blocks should snap onto the sequence next. But here's the cool part. The model doesn't just statically output the highest scoring raw math. It samples from the probability distribution. AI researcher Andrej Karpathy uses a great metaphor for this. He calls it flipping a biased coin. The tokens with the highest logit scores absolutely have a much higher probability of being chosen, but the model is still probabilistically sampling. It's rolling the dice. And this statistical roll of the dice is exactly why AI responses aren't just rigid formulas, but rather have natural, human-like variation. And finally, part 4, controlling AI creativity.
So, if AI text generation relies on flipping a mathematically biased coin, how do we actually steer that coin flip to control the output? We do it using temperature scaling. This is a crucial technique that divides those raw logic scores by a specific temperature value to adjust the probability distribution. Temperature is the literal mathematical dial that controls whether the AI acts like a serious, deterministic student reciting safe facts or a highly creative storyteller taking massive risks. When you manipulate this temperature, the results change drastically. At a low temperature, let's say 0.1, the output is confident and deterministic. It heavily favors the absolute most likely token every single time. At a medium temperature of 1.0, you get balanced randomness and natural human-like variation. But when you push the temperature high to around 1.5, the math completely flattens out the probabilities. The model becomes highly creative, risky, and might choose very random tokens to continue the sequence. Now, alongside temperature, we also rely on repetition penalties to guide the model. There is the presence penalty, which mathematically penalizes the model for using words that have already appeared, and the frequency penalty, which penalizes the model for overusing words too many times. Without these specific mathematical penalties, probability loops can easily trap the AI, causing it to repeatedly spit out the exact same tokens over and over again like a broken record. So we've broken down tokens, logits, and temperature scaling. But I want to leave you with this final provocative thought. If every single AI response, from writing complex code to crafting a beautiful poem, is ultimately just calculating the statistical probability of the next numbered token, what does that mean for human creativity? When we peel back the interface, it's just math navigating a massive space of overlapping chunks and biased coin flips. It certainly makes you reconsider the magic of your everyday interactions with these models, right? I really hope this explainer leaves you eager to learn more about the mechanics running beneath the surface.